All right, this next unit is going to be on a concept called gases, and it's in Chapter 10 in your textbook. And for many of you, this should be a lot of review because we did gases in honors chemistry. So the nice thing about this unit is most of this should be pretty much review, and a lot of the equations are pretty simplistic. They become a lot of plug and chug style problems, and even the conceptual types of questions most students have a pretty good understanding of just from real life phenomena that they've been exposed to their whole lives. So hopefully this is a part of this unit that goes much more smoothly than Chapter 5 did with enthalpy. All right, so the topics to be discussed will be on the top. I'm going to have 4 lectures, 2 this week and 2 next week, and that'll wrap us through this unit, so we're going to go through it pretty quickly. The first set of today's lecture is going to be in gas concepts and also introductory gas laws. And then later in the week, we're going to go through gas stoichiometry, how we can calculate volumes of gases produced from chemical equations. And then next week, we'll talk about gas mixtures and some other final concepts about gases to wrap up the unit. Okay? All right, so first of all, I want to just kind of show you this. So if we turn back to the first page that you have on your lecture notes here. So V, capital V in this class is going to stand for volume, and almost always you want to make sure that the volume is in liters for gases. The amount of a gas is symbolized by the letter N, which is moles. We're usually looking at the number of moles of a gas when we look at all these gas laws. The temperature of the gas must be in Kelvin. So if you're given a Celsius temperature, if you add 273 degrees to the Celsius temperature, that'll give you the Kelvin temperature. And we don't say degrees Kelvin, we say Kelvin. So for example, 25 degrees Celsius is 298 Kelvin. So we just say 298 Kelvin. Same temperature, just different units of measurement. But for gas laws, we always want to be in Kelvin. And pressure has enormous differently amount of units. And on the national exam, the two most typical type are ATM, which stands for atmospheres of pressure, or mmG, which is millimeters of mercury. Those are the 2 most prevalent on the national exam. There are others, and on the green sheet, they actually give you these conversion factors. 1 atmosphere of pressure is equal to 10,133 kilopascals, or 101 kilopascals, 760 millimeters of mercury, which is also 760 torr. So a torr and a millimeters of mercury is exactly the same thing. And PSI, they really don't talk about that much at all. But for us in the United States, we almost often talk PSI, specifically like air pressure in tires. Okay, you have a certain PSI measure that should be of a tire, of a properly inflated tire. So that's where the United States come in. But again, we primarily focus on the scientific community, and we're going to look mostly at atmospheres or millimeters of mercury. All right, real quickly, look at these pictures of these gas concepts. And real quickly, finish out and answer the questions. For example, number 1, what do you think the pressure in this container will be? Okay, draw the picture. Number 2, what do you think pressure number 3 is going to be? So if you real quickly pause the lecture, look at these different concepts and see if you can identify the relationships of the gases that are occurring through these different changes. All right, in the first one, you'll notice that the number of particle changes. We go from having 5 particles here to 10. So what we've done is we've doubled the number of particles, but kept the temperature the same and kept the size of the container same. You'll notice the word rigid. The word rigid means, for this unit, that the volume is constant. So think of like a metal container where the walls will not be flexible. Okay, they're going to stay the same volume of container. Okay, so if you double the number of molecules, what do you do to the number of collisions? You double it. So therefore, the pressure will be double. So the relationship is there is a direct relationship between the number of moles of a gas and its pressure. The more moles of gas you have, the more pressure you have. Whenever we have direct relationships in this class, they are proportions. Proportions show direct relationships. So the pressure and number of moles in the first set of conditions is equal to the new pressure with the new number of moles of gas. If you have direct relationships, you're going to have proportions. So in this problem, they said the pressures was 1.2 atmospheres. Well, what happens if you double the number of molecules? The pressure doubles. So if you put down 2.4 atmospheres in this new container, you are exactly correct. Doubling the number of molecules doubles the pressure. Okay, the next relationship is looking at temperature changes. Okay? So, in this case, we're going to keep the pressure constant. So what's going to happen to the molecules if they move faster? Well, I should say if the temperature is increased, their kinetic energy is increased, which means the molecules are moving faster. So these arrows are going to be longer, which means they're going to collide with the walls of the container with more force, and they're going to collide more often. So what's going to happen to my flexible container? So now this is like a balloon. So if I increase the temperature of a gas in a balloon, what happens to its volume? And hopefully you drew a picture of a balloon that gets larger. The molecules are moving faster on average. Now occasionally one of the molecules might not be moving faster, but overall the lengths of all the arrows averaged together would be a longer value. Okay? So because of that, there are more collisions with more force, and therefore the volume increases. So as temperature increases, it is directly related to the volume. As temperature goes up, volume goes up. It's a direct relationship. And therefore, again, because it's a direct relationship, we can get another gas law, which is V1 over T1 equals V2 over T2. This is called Charles' law. Charles' law states that if the temperature of a gas increases, its volume will increase if the pressure stays constant. So if we have a container that the pressure inside the room doesn't change, if I increase the temperature of the gas, the container will swell or get larger. Okay, that's called Charles' law. The first one is called Avogadro's law, where we look at pressure relationships between pressure and number of molecules. Okay, the third one is looking at something called Boyle's law. In Boyle's law, we keep the temperature constant, but we change the volume. We look at the pressure. The pressure and volume are changing. So here, the volume of the container is decreased by 1/2. It's 1/2 as big. So it went from 1 liter to 1/2 of a liter. The number of molecules of the gas stay the same. It's a fixed amount of gas. So what's going to happen with the number of collisions to the container walls? Because there is less area and the distance between wall to wall is less, the same number of molecules, while they're moving at the same rate of speed, they'll collide more frequently because the container has been reduced by 1/2 of its volume. Therefore, the relationship is as the volume is decreased, if the container is smaller, the pressure will be increased. There's an indirect relationship. And Boyle's law is the only indirect relationship that we study for all these introductory gas laws. Okay? So, as the volume decreases, the pressure increases. The equation for Boyle's law, then, is because it's an indirect relationship, it's not a proportion. Boyle's law is P1V1 equals P2V2. And this is something you should have studied in your algebra classes. When you have an indirect relationship, the product of the variables is a constant. When you have a direct relationship, the quotient of the variables is constant. Okay? So you just remember that the volume of the container is reduced, the pressure increases, and vice versa. The last one here, we have a situation where we have a solid. We have calcium carbonate put into an evacuated container. So an evacuated container, what that means for these problems is that the initial pressure of the container is 0. Okay? And you maybe be PI, initial pressure. So right now, if I remove all of the air and I put a solid in the container, there is going to be no pressure exerted in the walls of the container because there is no gas present. Okay? Now I increase the temperature of the reaction, which isn't going to change the pressure because I'm just heating a solid. But if I increase the temperature high enough and the solid undergoes a decomposition where it chemically breaks down into calcium oxide solid, so now the solid changes to calcium oxide, but it also produces a second product, which is carbon dioxide gas. So now, as this reaction occurs, I'm going to start to form gas in the container. Well, immediately, if I have a device called a manometer is a gauge that measures how much pressure is in a container. Initially, the manometer is reading 0 because the only thing that's in the container is a solid. But if we have a chemical reaction occur, and in the chemical reaction, a gas is formed where there wasn't one before, the pressure in the container will go up because now there will be gas in the container, which is going to cause pressure on the walls of the container. So you have to be very careful with reactions in which gases are formed or consumed, that pressure will change based on the number of molecules of gas. Another situation, this would be if I have a gas, let's say I've got 3 molecules of A, which is a gas, and it produces a molecule of B, which is a gas, and a molecule of C, which is a gas. As the reaction goes to completion, what's going to happen to the pressure of the container? Well, we're going from 3 moles of gas A for a total of 2 moles of gas for products. As the reaction proceeds, we go from a larger number of moles of gas to a smaller number of moles of gas. So when you look at chemical equations, you need to identify the gases in this unit because it's only the gases that produce pressure. So if the number of moles of gas increases, the pressure will go up. If the number of moles of gas decreases, then the pressure will decrease, just like we saw with example 1 at the top. Okay? So as the number of molecules change, the pressure in the container will change. All right? So those are some initial gas laws that I freehand picture that I have on this page that I just kind of inserted here. What causes pressure? When you think of pressure, what causes it? Now, first of all, we have to look at a state of material. If you have a solid material placed in a container, does that cause pressure? Well, the only place that we can see that, first of all, you have to understand what pressure is. Pressure is defined as force over a given area. Okay, so how much force applied over an area? So for a solid, the only place that it's exerting any type of pressure on it would be where it comes in contact to the bottom of the container, and that's mainly due to the weight of the material. Since we live on Earth and it has gravity, that weight of the solid is pushing down on whatever it contacts in that container. Okay? Same thing with a liquid. When I pour a liquid in a container, it also causes pressure, mainly from the mass of the material, the fluid. The interesting thing about liquids is that the pressure on the walls towards the top is different than the walls towards the bottom. This is called hydrostatic pressure, but this is something we're not really going to study in this class. This is more for physics. But as we get further and further down the liquid, the pressure increases because we have more weight of the liquid above us. Since there's more liquid above that next layer, there's more overall molecules weight, and that causes more pressure. So just like divers, if you ever dove deep down into a lake or something, you will feel more and more pressure the deeper you go because there's more water above your head. But for the sake of this class, we're going to say that solids and liquids really do not cause pressure in containers. Our focus is going to be on gases. When we have gases in closed containers, they cause pressure. Why? What causes the pressure? And the key concept you have to understand is it is the gas molecules colliding with the walls of the container. This is a very fundamental concept that you must get down, and you have to be very explicit when you describe pressure on the national exam that you make sure to make this connection. It's the collision of the molecules with the walls of the container. The more collisions you have, the more pressure you have. So collisions equals pressure. The molecules are colliding, bashing into the sides, walls of the container. And when they strike the container, that causes a force on that area. And then overall, all of that is called the pressure of it. So when we're looking at pressure, we're thinking about those molecules colliding with the walls. Here's a question that occurred on the national exam a few years ago. Why does pressure of a confined gas increase as temperature increases? Give 2 reasons. They explicitly told students in FRQ to give 2 reasons. Why does the pressure increase when the temperature goes above a gas? Okay, so think about that. Try to create 2 ideas right now in your head. Pause the lecture, and then see if you get both of these answers correct. All right, so let's see if you came up with them. The first one is, which I think most of you probably would get, that when we increase the temperature, the molecules of the gas move faster. Since the molecules are moving faster, let's say the molecules on average are moving the length of this arrow, but now at the higher temperature they're moving a longer arrow, indicates a faster moving molecule. On average, the molecules are moving faster, and because they're moving faster, that's going to cause there to be more collisions with the walls of the container. Okay? If there's more collisions per second with the container walls, there's going to be more pressure exerted. Okay? The second one students struggle with getting. They usually understand the first one. The second one, very few students get this one right. But hopefully now after you listen to this lecture, you'll get it right. When I increase the temperature, the molecules are moving faster. And because they move faster, they now have an increased kinetic energy. They have more kinetic energy, just like a vehicle. If a car is moving at 10 miles per hour, it has a certain kinetic energy. If it's now moving at 100 miles per hour, it has significantly more kinetic energy. So when a car strikes, let's say, an object, a tree, at 10 miles per hour, it exerts a certain force. But if it's moving at 100 miles per hour, it exerts an even larger force. So because the molecules are moving faster, the collisions with the walls of the container are more forceful. The molecules strike the walls with more force, more punch, and that causes a greater pressure too. So not only are there more collisions, but the collisions with the walls are occurring at a greater kinetic energy. That's why car crashes, the faster you're moving, the more chance that catastrophic events can occur, like even potential death. Okay? Okay, so we turn the page. So here you can see the gas laws that I wrote for you, Boyle's law, Charles' law, and the other gas law is Guy-Lussac's law, which is the pressure is directly related to the temperature. If the temperature goes up, the pressure goes up, and we kind of talked about that with that initial example. So you can see that for the direct relationships that you get a proportion. For an indirect relationship, again, you get a product. Now, these are two variable gas laws where all the other variables, number of molecules, number of moles of gas, and another variable are kept constant. The most important gas law in this unit is called the ideal gas law. In an ideal gas law, we treat all gases identically the same. You could have a problem with hydrogen gas, you could have a problem with carbon dioxide gas, you could have a problem with neon gas. Doesn't matter what the gas is. If we assume all gases behave ideal, and we'll talk about that later in the unit, it doesn't matter if the gas is in hydrogen or nitrogen. If you have 1 mole of each, you'll have the same exact pressure. It doesn't matter what the gas is. If we treat them to behave all ideally, they all are treated as equals. Okay? The ideal gas law is on your green sheet. These up above gas laws are not on the green sheet, but we can derive these other individual gas laws, okay, if we look at the ideal gas law. And the ideal gas law is PV equals nRT. P stands for pressure, and that can be in atmospheres, millimeters, mercury, torr, kilopascals, any units. The volume, it has to be in liters. N is the number of moles of gas. So if you have a mass of a gas in grams, you got to first convert it into moles before you can plug it in. You cannot plug grams in for N. You got to plug in moles. R is called the gas constant, and you do have these on your green sheet. On the green sheet, they are given to you, and you can look up which value of R you need. Okay? There are other and T is the temperature, and it has to be in Kelvin. So if you plug all the variables in, usually in a problem with the ideal gas law, one of the variables is not known. You plug in the other 4 variables, and you solve for the missing variable. Okay? For example, in the ideal gas law, if you're trying to solve for V, you would divide the P over, and now the pressure would be on the bottom. Same equation, just solve for V. And now if I plug in the moles, the gas constant, the temperature, and the pressure, I now will get the volume of that gas. I could solve this equation for any of the 5 variables. Okay? The gas constant R can be calculated from experimental values of pressure, volume, N, and T. So if I take the PV equals nRT and I solve it for N, I'm going to move the moles and the temperature over by dividing. So the gas constant is PV over RT. Well, if I plug in, okay, if I have, it is found that 1 mole of gas, any gas, if it's an ideal gas, contains 1 atmosphere of pressure. So 1 atmosphere is the pressure. 1 mole of gas is found to reach a volume of 22.4 liters if we have 1 mole and we're at 1 atmosphere of pressure. Okay? Oops, this is not supposed to be R. This should be an N. So we have 1 mole of gas. And the temperature, we don't plug in 0. That's why we do not plug Celsius into these gas laws, because 0 is a very common variable. 0 degrees Celsius is 273 Kelvin. So you have to remember that the volume has to be in liters and the temperature has to be in Kelvin. If we go ahead and multiply this out, we get 0.0821 atmospheres, liters over moles Kelvin. This is the ideal gas constant, and we will always use this value for the ideal gas constant whenever we are looking at a pressure in atmospheres. So the important thing with the ideal gas constant is you have to pick the right R value based on what the pressure units are in. So if the problem has got units of atmospheres, you will always use the R value of 0.0821, and that does not change. It's a constant. Okay? So whenever pressure is in atmospheres, you're going to use 0.0821 for its value, because the units are atmospheres, liters, moles, Kelvin. And this is why I said the temperature must be in Kelvin, the volume must be in liters, and we're using 0.0821 whenever we are in atmospheres. If your problem is in millimeters of mercury, you're going to use 62.4. And now the units are millimeters of mercury, liters per mole, Kelvin. So the R changes whenever the units on the pressure changes. So the key thing is to match up the pressure units, and that'll tell you which R variable to use. Okay? If, one thing to note, millimeters of mercury is equal to a torr. So if you have a problem that's in torr, you're also going to use 62.4. But now it's going to be torr liters per mole Kelvin. Okay? Now, as I said before, the other gas laws like Boyle's law can be derived from the ideal gas law. If I solve the ideal gas law for N, PV over RT is equal to N, in most of these problems, the amount of gas is fixed. So if I keep the N variable the same, and on one side I've got the pressure, volume, R, temperature for the first set of conditions are equal to the second set of conditions. Well, if I get rid of and set both of these equal to each other, first set of conditions, second set, since the number of moles of gas is the same, I can set these two equations equal to each other because the number of moles of gas has not changed in the problem. Well, if I set these equal to each other, you'll notice that the R, because it's a constant, doesn't change. It factors out of this equation. And if another variable is kept constant, in Boyle's law, the temperature is held constant. So T1 and T2 are exactly the same number. We can cross that out, and you'll notice we end up getting Boyle's law. We can get every gas law from the ideal gas law, mainly by factoring out all of the other variables that are kept constant. So you don't have to memorize all these gas laws. You can literally use just all of the, you can use ideal gas law to derive any of these gas laws that you want. Most of you are going to memorize these gas laws just because you're going to use them so frequently. Okay? All right. So gas laws, you need to be able to apply all of those. So if I turn back a page, if I've got constant volume and constant number of moles of gas, I'm using Gauss-Six's law. Your homework for the problems, I've given you like 6 or 7 practice problems, and then there's also an online homework. The online homework is the more important homework, but I would strongly recommend that you do some of these practice problems because you'll have a quiz on the ideal gas law late in the week. All right, so do these practice problems. It should not take you more than maybe 10-15 minutes. I have the answer key supplied online. So do these problems and then see if you are understanding how to do these simple plug and chug problems. I'm going to do an example for you right now. A rigid gas cylinder with a volume of 2.5 liters is found to be at 3.45 atmospheres of pressure at 25 degrees Celsius. How many atmospheres of pressure would be present in the cylinder if it were exposed to a heat source at 285 degrees? Okay? Key word in this problem is rigid. So what does that tell me? The volume is constant. So this problem is looking at atmospheres is pressure, Celsius is temperature. We are looking at, and we have a temperature 1 and we have a different temperature. And they're asking us to figure out what the new pressure would be. We have a problem here where we have a rigid container, so the volume and the amount of gas is fixed. So with that, we're trying to look at an equation in which, what equation do we use whenever there's a constant volume? So based on this problem, I would use his gas law, because what we're looking at is what's going to happen to the pressure if the temperature is increased. Well, right away, another way of figuring this out is you should be thinking, well, if I have a fixed container which doesn't change its volume, if I increase the temperature, the molecules can move faster, the temperature can go up. The pressure and temperature are directly related. So if it's a direct relationship, I can just simply use a proportion. Okay, so 3.45 atmospheres. Okay, the temperature in all these problems has to be in Kelvin. So we have to add 273 to all these numbers. 285 degrees is not Kelvin. We still got to add another 273 to that. We're trying to figure out what the new pressure will be when we increase the temperature up to 285 degrees. Key thing, the temperature must be in Kelvin. All right, so now we just do good old cross multiplication and solve. Okay, so 25 plus 273 is 298. So we have 298 times P equals 3.45 times 285 plus 273. Make sure to put that in parentheses. 1925.1 divide by 298. And our pressure now is 6.46 atmospheres. Okay? So that's how we use the gas law problems. If we have a change in pressure, temperature, or volume, we're going to be using one of those introductory gas laws. Okay? And if we only have one set of conditions, then we might be using the ideal gas law. Okay? So go ahead, give a try to problems 2, 3, and 4 on all the different variables that you have. What equation should I use? And then go ahead and plug and chug into those appropriate gas laws. All right, so go ahead and do these practice problems. Again, after that, I have a homework in mastering, which is primarily a lot of concept questions. And then there are some mathematical ones as well on gas laws and gas concepts. Okay, so go ahead and do that. I am opening up the chance that you can do the homework problems multiple times, and the highest score will be kept. I know some of you are starting to do that. A great way of trying to improve your form of score and get it up as high as possible. All right, thanks for listening. And then the next page is 5, 6, and 7. Try to figure out what gas law you're going to use based on the values given. Okay, write